Very good morning to all of you, my dear friends, and welcome back in this video lecture. Today we are going to learn some new things about bioinorganic chemistry, and the topic is electronic and geometric structures of metal ions in biology. Okay, so this is quite similar to that we have learned in inorganic chemistry or in coordination chemistry specifically. We know that different metal ions are having or they are existing in different coordination complexes. They are with different d-electron count. Okay, means depending on the type of ligand, depending on the geometry of the molecule, depending on the shape of the molecule, depending on the different atmosphere of that coordination complex of that metal, the metal cation, these are generally they are from the transition metals, that is d block elements. Okay, and they are having different d electron count. Okay, so here some metal ions have been shown here with their different oxidation states. Okay, and their d electron count is depicted in this here. Okay, so for example here vanadium metal cation. So vanadium, when it is existing in +3 oxidation state, the number of d electrons in this vanadium 3+ is 2. In vanadium 5+ oxidation state, the number of d electrons are 0. Here for chromium 3 it is 3, for molybdenum 2 they are 4, for molybdenum 3 the d electrons are 3, and for molybdenum 4 the d electrons are 2. So for manganese, copper and zinc in different oxidation states have been shown here in this fashion. Okay, so how these d electrons can be counted? Okay, it is very simple. Just we have taken one example for manganese, in which manganese is existing in +2 oxidation state, Mn2. Okay, so in this Mn +2 oxidation state, so here in this table it is shown that 5 d electrons are present. So how it is calculated? Okay, so it is just calculated as subtract the oxidation state from the atomic number of that metal. Okay, so manganese atomic number is 25, so 25 minus the oxidation state is 2, and minus the nearest inert gas or the previous inert gas from that manganese. Okay, so it is argon. Okay, and it is 18, argon 18. So 25 minus 2 it is 23, 23 minus 18 it is 23 minus 18 it is 5. So that's why manganese 2 is in manganese +2, they are having 5 d electrons. Okay, so that's why this is the different metal cations having different oxidation states, and their d electrons count has been depicted in this figure. Okay, now in these metal complexes which are found in biology or which are found in bioinorganic chemistry that we can studied here. Okay, different metals are having different ligands with different coordination numbers. So the majoritically the coordination numbers are 3, 4, 5 and 6. Okay, so in this way when the coordination number of that central metal ion is 3, the possible structures are 3, and these are trigonal planar. Okay, having bond angle 120 degree between the ML bond angle is 120 degree. So okay, so this is trigonal planar structure with coordination number 3. Then the another possible structure is pyramidal. Okay, it is just like ammonia, pyramidal structure. Okay, and the last one is T-shaped structure. Okay, so it is T-shaped structure. The bond angle is around about 90 degree. Then with coordination number 4, there are two possible structures. One is square planar and another is tetrahedral. Okay, so for square planar, the geometry is square planar and bond angle is 90 degree. For tetrahedral shape and the bond angle is 109 degree. For coordination number 5, the possible structures are again two. The first one is square pyramidal. Okay, this is a square base is there, and one fifth ligand is existing, or it is present at the apex of this square. Okay, it is called square pyramidal. 1 2 3 4 5. So 5 ligands are there, means we call it as a coordination number 5. And another possible structure is trigonal bipyramidal. So 3 ligands are in they are forming a basic triangle. Okay, and one is, they are called equatorial bonds or equatorial ligands at the base of a regular triangle, and the fourth and fifth ligands, they are existing at the above and below the plane of that base triangle. Okay, they are called axial ligands, or they are called axial bonds. Metal ligand bonds are called axial bonds. Okay, so the bond angle between the axial and equatorial ligands is 90 degree, and between any two equatorial ligands, they are 120 degree. Then the last possible and very oftenly found, the coordination number is 6. These are the very usually found metal complexes with coordination number 6, and very well known structure or geometry of these coordination 6 geometry is octahedral. What is the name of this geometry? Octahedral. Okay, so this is octahedral geometry. Okay, the bond angle is 90 degree between two ligands. Okay, so this is the electronic and geometric structures of metal ions in biology. Now, in this can be, or how it can be concluded that in a specific metal cation, when it is present in biological system, when it is present in specific protein. Okay, so what is the geometry of that metal cation? What is the D9? What is the d-electron count of that metal cation? That how it is concluded? That can be concluded with the help of the ligand splitting pattern or ligand splitting factor. Okay, in the different possible tetrahedral, square planar and octahedral ligand field. Okay, that we are going to see. Suppose we have a D9 electron D8 or D9 electron configuration of a metal cation, for example nickel. So nickel 2 plus is in D8, is with D8 configuration. Okay, nickel 2 plus, for example nickel having atomic number Z is equal to 28. So electronic configuration can be written as argon gas configuration, and 3d8 4s2, 3d8 4s2. So argon 18 plus 2 20 plus 8 28. Okay, so when nickel is existing in plus 2 oxidation state, so the valence 2 electrons from the 4s subshell has been removed, and we have argon gas configuration and 3d8 configuration. So how many d electrons are present in nickel 2 plus? They are 8. So how these d8 electrons, they have been distributed in the different ligand fields, and these are octahedral, tetrahedral and square planar ligand fields. That can be that we have to discuss here. Okay, so these can be depicted here. We know that the ligand field splitting pattern that we have already seen in the inorganic chemistry or in coordination chemistry is like that. So in octahedral field, in tetrahedral field and in square planar field, square planar ligand field. These are different, there are different splitting pattern can be observed. In octahedral field, the T2G electrons are having lower energy. Okay, so energy is increasing from bottom to top. So these are T2G set of electrons. T2G set of electrons. T2G means dxy, dyz and dxz set of d orbitals. Okay, and this is Eg set of, these two orbitals are Eg set of d orbitals. Okay, they are called, they are having higher energy in octahedral field. The situation is get reversed in tetrahedral field, means the Eg set of d orbitals are having lower energy than that of T2G, One more point here that can be emphasized here, this is the distance del O, this is the distance, that is the distance of separation between T2G set and Eg set of orbitals is designated by energy difference of del O, and in this tetrahedral field it is indicated by del T. Here O stands for octahedral, T stands for tetrahedral. Here the large difference is there between T2G and Eg set of d orbitals in octahedral field, whereas del T is very small as compared to del T. In square planar ligand field, the metal cation is approaching to the ligands in different manner. Okay, so that's why the splitting of these d orbitals has been taken place in different manner. Okay, so let us take here the ligand is approaching in xy direction. As the ligand is approaching in the x and y direction, so there is a large much repulsion has been taken place between the electrons of d orbitals of metal cation and the ligand's electrons. Okay, so that's why the x and y component of the d orbitals, they are having highest energy or they are repelling very much. So that's why, and d component of the d orbital, z component of the d orbital is approaching in the opposite direction so that's why the energy of the z component of the d orbital is less. Okay, so dxz, dyz and dz square, they are having lower energy. Okay, so these are dxz and dyz orbitals. Okay, and this one is dz square orbital of the central metal cation, whereas xy and dx square minus y square, they are having higher energy. Okay, so 1 2 3 4 and 5 d orbitals have been shown here. Now the d8 electronic configuration of the central nickel 2+ metal cation, how these d electrons have been distributed in a different ligand field, that we have to see here. Okay, so we have to place these 8 electrons in according to above principle, Hund's rule and Pauli's exclusion principle. Okay, so 2 electrons will be placed here next to, or we can say that 1 2 3 electrons, they are having same energy. Okay, then 4 5 6, as the difference is very large, so the electrons will go to pairing, so 6, then 7 and this is 8. Okay, so in octahedral field the d8 electrons are in the, they are placed in this fashion. Okay, so this is indicating that there are 2 unpaired electrons present, and due to these 2 unpaired electrons, this system is paramagnetic. This system is paramagnetic. Why it is called paramagnetic? We know that whenever there is a presence of unpaired electrons, we can say that that system is paramagnetic in nature. So as there are 2 unpaired electrons, the system is paramagnetic in nature. Now in case of EG, in case of tetrahedral ligand field, the situation is different. Okay, so 1 2 3 4 5 6 7 and 8. Okay, so this is the case of D8 configuration of nickel 2 plus metal cation. Okay, again there are two unpaired electrons present in T2G set of d orbitals. Again we can say that this system is also paramagnetic in nature. Paramagnetic in nature. But in case of square planar ligand field, the situation is different. Okay, and it is just like that: 1 2 3 4 5 6 7 and 8. So all the 8 electrons are in 4 pairs. 1 2 3 4, all are paired electrons. So all electrons are paired in square planar ligand field, so we can say that it is diamagnetic in nature. We can say that it is diamagnetic in nature. Now what is the use of this study, or how we can say that, what is the purpose to study such type of analysis? So when a metal cation is if it is present in a specific protein, and that specific protein, the magnetic property of that specific protein is found by experimental, then if that experiment is showing that metal complex which is found in that specific protein is diamagnetic in nature, and that metal cation is having D8 electronic configuration. Okay, so this figure is indicating that that protein complex is diamagnetic in nature, and it is having D8 configuration. So out of these three possibilities, only this possibility, which is having square planar geometry, is in diamagnetic in nature. Means that conclusion can be drawn that in that protein structure, the metal center is having square planar geometry. This is the conclusion that can be drawn from this study. Okay, so in this way we have taken here only D8 configuration of a particular metal cation. Okay, and in this way we can determine the different geometries of different metal centers in different metalloproteins or metalloenzymes in biological systems. So this is the way of finding out the geometries, electronic and geometric structures of different metal ions in biology. So this is the method that how we can judge to a particular geometry, electronic and structural geometry of the metal centers in biological systems. Okay, so this is all about the today's lecture. Thanks a lot for watching this video. Have a nice day.